right. All right. How's it going, everybody? So let's see. We wanted to, we kind of decided in the last, 40-ish minutes that we were going to talk about some modal formulas today. So I can maybe start us off with that discussion. So how much do people know about modal formulas and modal logic before I start just saying everything?
I don't know much.
Don't know
Yeah,
much.
I haven't heard of it.
Yeah, all right. Well, I mean, I'm in the kind of a similar spot of I don't know all that much. I'm very new to all of this modal logic business, but essentially it gives us a language to express behavioral properties in terms of um, just the way we have Boolean logic to do certain type of reasoning. This is just a language to express certain behavioral properties of a system. So typically people are talking about like label transition systems, so like pretty general stuff when they're talking about this. But of course, any rolling program can be interpreted as a label transition system. Where the transitions that are happening are like whatever reductions are going on, like a comma event or match or something along those lines. Josh and I were talking a little bit about what exactly are the transition systems and what exactly are the transitions in something like rolling. So like in RoCalc, there's really only one label for a transition, and that only transition in RoCalc is the comma event. Like that's the only way to evolve the state of a RoCalc term or program or whatever you want to call it. But in rolling, we have comma events and maybe there's even different flavors of comma events and then also some other things to do reduction. So it's a little more complicated in the rolling setting. But at least in RoCalc, it's fairly straightforward.
Can you say more about when you say reduction? You imply some kind of smaller set from where you started?
Oh,
because I was listening about modal logic that there is something that they say must be like smaller or
yeah.
that sense.
Yeah, so in modal logic, they always talk about like what's a valid formula, basically. So like there are these fixed point operators. One's called the minimal fixed point operator. One's called the maximal fixed point operator. We'll talk about that pretty soon. But basically, these operators only have solutions for certain types of formulae, and that's basically for a monotone formula. And
yes.
Yeah, and so like a monotone formula. So essentially, all we're doing is we're expressing some property. So like I said, we're talking about label transition systems, right? So label transition systems have several things that we're keeping track of. So like states are changing, and those are kind of like at least visually, the way that I think about it is like the states in a label transition system are kind of like vertices in a graph or something, and then the transitions themselves are like directed edges. Basically, they're labeled, of course, because we can have different flavors of transitions. But essentially, with the modal formulae, we're talking about sets of states in a label transition system, and then kind of asking a question like, here's a formula that's expressing some property, like what set of states in this label transition system is going to satisfy this property, essentially. So the only properties that make sense to discuss are properties arising from what we call a monotone formula. And a monotone formula is basically like, I want to apply it to some set of states, and I want to get a set of states out of it. And it's monotone if I take some bigger set and put it into the formula, and it gives me more states as the output, essentially, or like, a superset of the original thing. So like if I have
a clarification on that. is it just bigger, or does it have to be a superset?
Yeah, I think it has to be a superset. Otherwise,
That's a different set that happens to be bigger.
yeah. Otherwise, we got to get into a discussion of like cardinality or ordinality or something like that. And nowhere have I seen any discussion of that sort of thing. So I think here we're really talking about like supersets. So like literally contained in. So like if I take some set A that's contained in another set B, I apply this formula to both of those things. The set of states that comes out of applying the formula to A should be contained in the set of states that comes out of applying the formula to B. So that's my interpretation.
Yeah, that's what I thought.
Okay, cool.
And how is this related to reduction? I mean, is it monotone but other way around? Because
yeah. So I'll give you my interpretation of how it's related to reduction. So reduction might be a slight misnomer because we're not getting less things out of like a particular term or set of terms that we're looking at. Maybe I don't know why they call it a reduction. But either way, yeah. So we're talking about events, right? Like, yeah, I mean, it's possible to start with one term and have many reductions coming out of it, right? So like, clearly we're not like getting less things in like a reduced term. So let's see. But either way,
okay. I think the word reduction corresponds to how, like reductions in process calculus, like common, the row calc or pi calc, or what is it called in lambda calc? Is it beta reduction?
Yeah. They also call it reduction there as well. Yeah, I don't know. I guess maybe reduction really just means like computation, but either way.
Yeah, maybe that's a great point. Think of it as computation.
Yeah, I mean, there's different kinds of reductions, like the alpha or the lambda calculus. The beta reduction is substitution.
Yeah, right. Yeah, so let's see. Joshy, did you have anything to add to what I was saying about modal formulae so far?
Well, I jumped in a few minutes late, so I don't know if you said this, but the big picture that I've been thinking of, and maybe this is right or maybe it's not, but I think it's at least close, is that we're going to use these modal formula to express things like at some point there's going to be a certain kind, like an A reduction available or a COM reduction available, or we might express something like there are no more reductions available, or something like this. And so we're going to use these as the basis of like what Greg always calls behavioral types.
Yeah,
so
exactly.
Once we've been really in the weeds just learning like how to express things. Like I still find it challenging to be expressive sometimes, especially with the fixed point operators. But I think the holy grail then is like once we can express these things, we can just say like, okay, given some state, like, and most likely that's going to be some row calc program or row lang program. Does it satisfy this formula? Like, does it do or not do whatever thing I expressed with one of these modal formulas?
Right. Yeah. Yeah, exactly. And all of this stuff is like formalized in the namespace logic paper, at least for row calc. I don't know exactly what the transition to like row lang and maybe some different transitions possible, how that changes the situation, but
can you link that picture?
Yeah, I can. I'll send something to the Discord afterwards. Either way, let's see. I'm trying to think of a good place to start. Because I mean, so why are we talking about this stuff? So basically, it comes down to sort of what Joshi was saying is we can capture some behavioral elements in these formulas, and essentially what we can do is capture something like a safety condition or a liveness condition in terms of these modal formula, and that's why we're interested in it specifically for consensus.
So is this like approaching on correct by construction?
I think so. I don't know a super formal definition of correct by construction. To be totally honest with you, I think it is though.
Yeah, I would say it's very much in line with correct by construction to have formal proofs of like here are all of the allowable behaviors of my system. But again, I'm not sure what exactly the definition. People kind of just throw that term around.
Here's a hypothesis. Maybe the correct by construction portion is the portion that Greg did in the namespace logic paper. And now, like, by being able to write these kinds of formulas about our programs, we're sort of like capitalizing on the fact that it is correct by construction. Yeah. I don't really know. I don't know what part of the process is which.
Right.
Go ahead.
So it means that you can have two pieces proven correct and put them together and get a constructed piece, I would think. When you're looking at it in that way, it's correct by construction. Which is, I guess, orthogonal. Behavioral.
Yeah. So I gave a talk at DevCon last year, and he was saying that correct by construction, you can think of it as like partial application functions or partially applied functions that produce sets. And, so each time you can apply another parameter to the set, and the set, either grows or reduces monotonically. But the point is that each time, you're guaranteed all the previous proofs that you've created, and you're just partially applying to that set and creating smaller sets.
That's an interesting thing to think about.
Yeah.
Yeah,
I like that talk.
It almost sounds
glad you said.
Yeah, I mean, from what Jay and Jim just said, it almost sounds like correct by construction somehow has to deal with the compositionality or something, or maybe I don't fully understand what we even mean by compositionality, but that was kind of my understanding of it.
Yeah, you can combine sets of behavioral rules. A regular manner. I mean, whether it makes sense or not is something else. But if you can combine them, they're correct by construction.
All right, so I'm trying to think of a good place to start. So you think maybe we should start with just like what is Hennessy-Milner logic, and then kind of go from there. Like, what's the validity of a formula, et cetera, et cetera.
Yeah, I think that's a good idea. We can go fast or slow as necessary, and definitely I'll be ready to go slow by the time we get to fixed point operators.
Yeah. All right.
Can you maybe say? Can you maybe say about different types of modal logic? As I understood, the possibility and necessity is only like one way of looking at the modal logic, right? It's or is it the most popular way of looking at modal logic? But there's many different modal logics, temporal or different kinds.
I don't know the answer to that. I know this whatever flavor we've been studying is often called the modal mu calculus. Yeah, is necessity and what was the other one you said? Inevitability or something? Or possibility.
Possibility. Yeah.
Is that's like the diamond and box modalities?
Yeah.
Yeah. Okay, gotcha.
And I heard that this is like the most popular one, and this is why this is called modal logic. But it's not. It's only like one way of doing modal logic.
Yeah, that's cool. I didn't know that. So necessity and possibility. I wonder. Diamond is like necessity. Like there definitely exists something, and actually, I'm not too sure. How did that work out?
No, box is. a necessity and diamond is a possibility, I think.
I almost
well,
think of those more as like there exists and for all, as opposed to, because there's a way. Oh yeah, go ahead.
Well, I mean well, but with that interpretation, I think what Tomislav said makes sense, right? Like with the box, we're saying if there exists, you know, some A transition or whatever, then it must satisfy this formula. So that's kind of like the necessity condition.
But diamond is the one that guarantees that some such transition definitely exists, right? If I say like diamond A, that means definitely there must be an A transition. Whereas as box A still allows it not to be.
I don't know, man.
Oh yeah. Okay.
Yeah. All right. So let's see. I guess I'll share my screen so we can have some common stuff here. Just like with row calc, you know, we have a logic, so we have to define like what are the terms in our logic. So for Hennessy-Milner logic, we're talking about formulae, so I'll just call them capital F when I talk about them. So in terms of like BNF grammar, our possible formulas are true. True is just like, so we're talking about well, okay, I guess not yet, but true is just like anything satisfies the true formula. For you know, false, nothing satisfies the false formula, basically. We can have, if we have a formula, we can have a negation of our formula. So I don't know, maybe something like negative F if we have an F.
And this is all a part of Boolean logic, right?
Yeah.
It's the same.
Exactly. It's exactly the same until we get to the modal operators, which are coming up in 1 second. So we have ands, we have ors, two formula, and then we have the diamond modality for some action and some formula afterwards, and then we have the box modality with some action and some formula afterwards.
I have a question.
So those, yeah, sure.
I must ask you about from where this A comes from. I mean,
yeah,
you don't have to write.
So I don't think so. A doesn't have any connection to the formulas themselves. In it, like, and when I say that, I mean something like there's no connection between A's and F's in the way that there's a connection between like names and processes and row calc. So the way that I was taking this, because honestly I didn't even really think about it so much, but I kind of just was taking these A's to be like, we have some set of actions and we can use them whenever we want, kind of like names and PyCalc or something like that. There's just like always this set out there, and we can use it if we feel like, but we don't have to. And typically when we're talking about a specific transition system, we have a set of transitions that we can use, and then these will correspond to the set of transitions in that system.
Oh, you mean set of transitions? This A represents a set of transitions, like actions.
Oh yeah, so the little a is just like a single action or a single transition.
Oh, okay.
Yeah,
and this will be a rolling term, right? In our case for Roland, we are interested to place this in this place of A rolling term and make some logic with rolling terms.
Oh, so what I was thinking is we were replacing this A with like a com event or something like that, because those are our transitions in, you know, row calc, for example. That's the thing I think I understand the most. So, you know, we would say something like, you know, diamondcalm and then some formula. And essentially what we're asking is, does the term that we're looking at have some com event out of it in which, you know, that resulting state satisfies this formula that we have on the right side of the diamond, basically.
This is like an extension of com events, in a sense. You're not doing com events like immediately, but you have something else that you do, and then you will do com event.
Mm-hmm. Yeah, so that formula, like on line 8, basically says like you're talking about some state right now, right? Some row length term, and then so like if it's diamondcalm F, then it says like, is this state such that there's definitely a COM event, and then the resulting state after that COM event satisfies F. So yeah, totally. It requires like, you know, in some case partial and in some case complete and in some case none, like reduction of the state to see how it evolves as time goes by.
So yeah, this can be if doesn't make COM event, then do something, right? Mm-hmm. Not only to make COM event.
Yeah.
Yes. So like if we're asking diamondcalm F about some state, if that state doesn't reduce at all, then the diamondcalm, that means like there must exist a COM event, and if there doesn't, then right away that formula is not satisfied.
Cool. Yeah, so we can write down a rule like you know, diamondcalm false, and then ask ourselves like maybe what state could possibly satisfy this.
And false means
false means no state satisfies this formula.
Okay.
Yeah, so maybe so that's just syntax that we have currently, right? So maybe like in terms of semantics, this is like there exists an action or transition or whatever, I guess I could say such that after applying F is true. Or, you know, whatever this formula F is, the state that we're now in after applying this action A satisfies this formula. And then a similar thing here, but this is, you know, for all A, for all actions.
Oh, so when you say false, you cannot. It's not possible to get into this state. This means false.
Yeah, exactly.
Oh, cool.
Yeah, so I don't know if those explanations are clear, but yeah, like you just said here. So this is like if there, you know, if we apply some, so there is a COM event, and after we apply it, we get false.
In the second one, what does that mean? For all actions A out of the state F is satisfied.
Yeah, so
I think satisfied is a better word there. F is satisfied, because F is like some formula or constraint, and then we can say like, does this particular state, which means in our case, like, does this particular row calc term satisfy this formula F?
Yeah.
So hey, Isaac, should we just write a couple little terms up there, like simple 1 or 2 sends, or maybe one that has a couple comms or whatever?
Sure. Yeah, why not? So like x and 1. Is this what you're talking about?
Yeah, totally. Then we can write some formulas, and you say like which ones satisfy or something.
Okay. So here's a term. Let's see what we're looking for exactly. Yeah, all right. So I'm not 100% sure what I want to write here because I'm not sure what I'm going for, but I'll just write some formulas and we'll see what happens.
Well, okay. In the meantime, let's think about whether the state on line 13 satisfies the formula on line 11, right? Yeah. So that's the kind of question we care about asking here. So it's always going to either be a yes or no answer. Like yes, the formula is satisfied, or no, it's not. And so, like I guess the first question, line 11's formula says there must be a COM event where the post state satisfies false. So in line 13, there definitely is a COM event, right? In fact, there's exactly one possible COM event. And so then we have to say, does the post state satisfy false? So like, well, what is the post state after we do the COM event in line 13? Well, it's just nil. It's just the stopped process. So now our question is, does nil satisfy false? And the answer is no, nil doesn't satisfy false because nothing satisfies false.
Mm-hmm.
And so then we can say that line 13 does not satisfy the formula on line 11.
But how do you make formulas that concern actual state? Like, you know, we could say COM true on line 11, and that still doesn't, it's not really useful. Like, how do we make formulas?
No, that's a great one. Yeah, COM true is a great one. So that formula
COM true is even better than COM false, actually. Yeah. All right, let me spoil COM false, or diamond COM false at least. This is no state satisfies this formula, because basically what we're saying is, you know, if there's a COM event, then the resulting state has to be false, so there can't be a COM event. And if there's not a COM event, maybe I'm saying this wrong, but either way, this is equivalent to just to false. But this is much more interesting, because what are we actually saying here? We're saying, well, okay, there's a COM event, and the resulting state could basically be any process you want.
Okay. So it's just verifying that a COM event did happen.
Yeah, so then this is basically just expressing that there's at least one COM event that can happen in, you know, for this particular term, right? At least one COM event.
At least, or just one?
Well, we have guaranteed existence of one of them, but certainly if there are two possible COM events, then it would also satisfy this formula. Right, and then, I mean, we could say something like, you know, diamondcalm true, and now we're asking for states that have two COM events, or at least two COM events. Okay, how about something like, maybe we should do something with the box modality. Do boxcalm false.
So that says for all COMs false.
Right. Yes. So basically, if there is some COM reduction of our term, then it has to result in a false formula, or satisfying a false formula. So no term can result from this thing in a COM event.
So on line 16, we couldn't have the result of false.
Yeah. So line 16 doesn't satisfy this one, right? Because, well, there was a COM event. Here it is. The resulting state was nil. Well, that doesn't satisfy the false formula.
Well, if you instead of nil resulted in false.
Oh, you want like the Boolean false here?
No, I want to reduce to false. Yeah.
Okay.
Instead of nil, false.
What do you guys think about this?
But this is not the same false.
It's not the same false, yeah.
But false in Roland is just...
Yeah, this is like the formula false, and this is like the process false.
Sorry.
So false in the formula is like the void type, like you can't actually access it from any state.
Yeah, exactly.
And if we only have a send, for example, or nil in our Roland term, this will not make a COM event. So in that sense, satisfies the formula.
Yeah, right, exactly. So here's a term that doesn't even have a COM event, so it just trivially satisfies this formula, right?
Okay.
Yeah.
Does it satisfy the first one?
Does it satisfy this one?
Yeah.
Well, should this send on one satisfy the first formula?
Well, the formula on line 11 says there exists a COM and the post state satisfies false. And in 18, there doesn't even exist a com, so I say no.
Yeah. Yeah, I would also say no. Yeah, I mean, well, and like I said, this one is literally equivalent to false. So literally nothing should satisfy this formula. Yeah, so another silly identity in Hennessy-Miller logic would be something like, and this is in general true with any action in a label transition system. But if I ask, for this formula, like boxcalm true, and what states satisfy this, it turns out that all states satisfy this formula because this is just true.
Yeah.
So if there exists a COM event, then the post state satisfies true. Well, if there didn't exist a COM event, trivially true. If there did, well, the resulting state is just any possible row calc term. So of course it's true.
So for line 9, maybe we could change that to just all actions A out of the state F are satisfied. Because that was my confusion. I was trying to parse that sentence.
State. Maybe with a comma there, is that better? So the state that I'm talking about is not actually written basically anywhere here, right?
Oh, okay.
Yeah, we want to ask like satisfaction of a formula for like given some state, we want to ask about satisfaction of a formula.
Gotcha. Okay, that makes sense.
Yeah, so these are kind of the states that we were talking about that we didn't picture up here.
Okay.
Yeah. Okay, cool. So that's kind of the essence of Hennessy-Miller logic is just regular Boolean logic, but then we also have this extension with the diamond and box modality, which essentially are just saying something about existence of these transitions out of a given state, or something along those lines, and what the post state will look like.
That formula you wrote in line 14, I think, is worth translating to regular English too. So
okay, cool.
For all comms false, and so that means like the post state after the com has to satisfy false, and we know for sure that no states satisfy false. So the way I take line 14 is to say that there are no comms possible.
Yeah. Okay, so there's some dualities between these diamond and box modalities. So maybe we should talk about that stuff. So like some logical equivalences between them. And essentially what it comes down to is like the relation between and or being dual relations. Like if I write down a grammar that only uses ands and trues and never says anything about false or an or, I can always get to an or by using negation and ands, and the same exact relationship holds between the diamond and box modality. And if you're familiar with existential and universal quantifiers, it's basically the same thing. And that's because we're saying something here about an existential quantifier, and here we're saying something about a universal quantifier, because they're saying there exists something in this formula and for all something in this formula, basically. Mm-hmm. So essentially what it comes down to is, I mean, if you think about it, if you were to negate something like, diamond A and some formula, it turns out that this is logically equivalent to taking the box of A and negating the formula. I believe that's right, yeah. And then also same way around, and we can talk about why those would be true. Diamond A, not F. Okay. Yeah, so here we're just saying it's not the case that there exists an A into which we transition into a state that satisfies F is logically equivalent to for all A if we transition using A, then that post state will satisfy not F.
Yeah.
And then basically the same exact thing for the other identity. So, yeah.
Oh, that makes a lot of sense. That was not nearly as clear when I encountered it the first time.
Yeah.
Yeah, drawing the analogy to the existential and universal quantifiers definitely helps a lot.
Yeah. I was going to say, if you're familiar with that stuff, then really this modal logic is not anything new. It's kind of just a new way of expressing those same ideas. So let's see. Okay, here's the moment of truth, right? So we can start talking about some fixed point operators now. And essentially what these fixed point operators do for us is, well, they're going to extend the grammar of this Hennessy-Milner logic with two more constructors, the minimal fixed point operator and the maximal fixed point operator. So let me give you the notation and then we'll talk about that stuff. So just go back up here.
Are they also dual, or?
Yeah, they're also dual in a sense. So this the minimal fixed point is usually written with a mu. Unfortunately, I'm writing with ASCII characters here, but either way, so we can write something along the lines of this, like mu x dot f, and this x here now is going to represent a set of these states, and this is the minimal fixed point operator. Okay, and then we also have the maximal fixed point operator, which people write with a new, same exact syntax otherwise. Okay, and this is the maximal fixed point operator. All right. And and also one last thing is we can talk about a set of states as well. So some trippy formulas that you can write down now would be something like mu x dot x. And now essentially, so what it means for a state to satisfy a formula like this is essentially going to mean that the state is in the set X. So here, this is a set of states. And so what it means for, let's just write down a definition first. So what it means for some state, which I'll write lowercase s. So what it means for a state S to satisfy some formula, say like mu x dot f, is basically to say that not only is this state in the set X, but also X is the smallest set of states that satisfy this formula, basically. So this is if S in X and X is the smallest set of states such that X is equal to F.
And smallest in this set, in this power set, right? Or
yeah, so we only have guaranteed existence of this smallest set, or this minimal fixed solution to the minimal fixed point operator equation, and vice versa for the maximal fixed point operator equation, if this operator is monotone, basically. And then,
so, but this means like the least amount of recursion, right?
Yeah, I'm not 100% clear on what is meant by all of this, but I mean we can do some examples and see what it means in those contexts at least. But I don't think I have a complete grasp of what is meant by smallest and largest. But like I said, we'll go through some examples and you'll see how the inclusion works.
The place where I'm feeling really stuck is distinguishing the mu and the nu and all that. And then like Tomislav, you said like mu might mean like the least amount of recursion, and I've definitely heard people say that like mu means only finitely many iterations, but I have not been able to convince myself that that's equivalent to what Isaac wrote on 27 and 28.
Yeah.
I believe it just because smart people say it, but I haven't seen it yet.
Mm-hmm. Yeah, I'd really like to find some just more resources, I guess, for this modal logic stuff, because I mean, basically it's just that Coursera course that I've seen so far, and then like whatever's in the namespace logic paper, but that's mostly assuming you're familiar with all of this stuff. So
I'll drop a really nice YouTube video lecture that I saw the other day, but it helped. I felt like it really helped, and it was nice to see another perspective, but I still didn't quite get the difference between mu and nu.
Okay, cool. Yeah, so let's do some examples with this mu and nu stuff. So let's talk about this formula here. So we have the formula mu x dot x. So essentially what we're doing is we're looking to satisfy, I mean, so our formula is x, right? We're looking to satisfy an equation like x equals x. Okay, but any set is equal to itself. So any set of states that we're talking about will satisfy this particular formula. So in particular, the empty set satisfies this formula. And so we say that the solution to this minimal fixed point operator equation here is actually just the empty set.
Okay.
And opposed to that, in contrast, right, we can talk about this equation nu x dot x. Again, we're still looking at the same equation to satisfy. We're talking about sets of states, right? And so we're saying we care about the largest possible set of states where all of those states are where, I mean, it's just equal to itself, right? So you might be able to convince yourself that the solution to this should be all states. So the set of all states. So whatever transition system it is that we're thinking of, if we were to ask, you know, what is the solution to this formula for that transition system, it would be all possible states in the transition system.
And mu is always subset of nu.
Yeah, that's right. Yeah, they say that this formula implies this formula, because like you said, the solution is always a subset of the solution to the maximal fixed point operator. And so it's a little bit strange, but what this tells us is that this formula mu x dot x is actually logically equivalent to false. And this formula nu x dot x is logically equivalent to true.
Oh, with the capital.
Yeah, sorry, with capitals.
Okay.
Yeah, whoops, wrong way. There we go. There we go. Just checking to make sure you're actually paying attention.
when you're saying the solution is empty set.
Yeah.
This set is really a representation of the state.
Yeah. So okay. So we're saying that if we were to look at an equation like x equals x, right? And I'm talking, so x is a set of states. So we can ask ourselves, what set of states is equal to itself? Well, any subset of all of the states satisfies this equation. In particular, the smallest possible set in terms of inclusion is going to be the empty set that satisfies this one.
I'm thinking in terms of rolling, this set is like a set of terms.
Yeah, right.
Yeah. Okay. Okay.
Yeah. So like a set of like a set of processes. Exactly. Yeah.
Wait,
Yeah.
can you explain why the mu x dot x equals false? Or that's equivalent to false.
Yeah. So we're saying we have a formula. We have a formula mu x dot x, and it is satisfied for no states, basically. So we have another formula that's satisfied for no states. That's just the false formula, right? So, and it's always true because, I mean, we didn't even say what transition system it is that we're thinking of when we get the solution to this is the empty set, right? So it actually turns out that this is completely equivalent to false, right? So as a formula, this always has the empty set as the solution, but that's exactly the same as the formula false.
Okay, that makes sense. We're kind of just translating formulas to sets of states.
Yeah, exactly.
Oh, I wanted to even say earlier that a formula and a set of states are really like the same thing, because for any given formula, you can think of the set of states that satisfies that formula. And for any set of states, you can think of the formula that describes these and only these states. So they feel like different ways of thinking about things, but they're always interchangeable with one another.
Yeah, and I think that's why the minimal and maximal fixed point operators are so confusing, because it almost seems like we're writing the same equations here, but somehow we're getting different solutions out of it, and somehow we have like some ordering of the solutions to like the equation that we're asking for here. So I don't know. To me, it seems confusing.
So one thing that I can show when we get there that I learned from that YouTube video is the algorithm to find the smallest and largest set of states. Because I don't know if you guys know the method of fixed point iteration for like finding roots of a polynomial, where you like take a guess and then calculate the slope and take your new guess and like you either get till you're close enough or you reach a fixed point and then you're there.
Mm-hmm.
And the guy from the YouTube video basically did the same thing. So you've got to write the equation like Isaac did on 31 and 34. And you know, in general, they're more interesting equations than those ones. And then you start if you want to find like the smallest set mu, you start by plugging in the empty set. And you say like, okay, what states can get me to the empty set? And then you iterate. So like, you know, this set keeps grows larger, and then you're like, all right, let's try it with that set. And then you get something larger, and eventually you reach a fixed point, and then that's this like solution for mu x dot x. And then it's just a matter of saying like, you know, we're ultimately what we're trying to say is like, does my state of interest satisfy this mu x dot whatever formula? So once you found that minimal set of state solutions, then it's an easy question. Is my state of interest in that set?
Mm-hmm. Mm-hmm. Yeah, that makes a lot of sense. And I don't know why, but for some reason while you were explaining that, I was thinking of induction and co-induction. And I'm kind of thinking of this mu as like an induction and this nu as like co-induction. Because at least from the way I understand it, like induction is basically like start at the least thing and then build your way up. And then co-induction is kind of like start at the greatest thing and build your way down almost.
Yeah, I've never heard the term co-induction before, but that's exactly what he did for nu. He said, instead of starting with the empty set and iterating, he said, start with true, you know, and then you'll get this smaller and smaller set. And when you reach the fixed point, that's your new solution.
Well, that actually makes a lot of sense because, and that also, I feel like makes sense for why mu only expresses something about finite iterations, because if you're starting at the bottom and then you're just like, you know, iterating out, like you're only ever going to go finitely many steps. And where nu can say something about infinite iterations, because if you're starting with the entire thing and then maybe like taking some stuff away as you go, you're only ever taking finitely many things away. So you can still be left with infinite collections. But I don't know. I mean, that's just intuition, I guess, from what you were saying.
Yeah, I think that'll be helpful. I'm confident we're going to make progress on my understanding today.
Yeah, great. Do you want to show that stuff, or should I show the?
I'd be happy to. I think we should do a simple example first, maybe like mu x dot diamond ax or something.
Yeah, that's the only example I know. So let's talk about mu x dot diamond ax. and new x dot diamond ax. And I'll show you the, I'm not sure how I'm going to show you the system that we're dealing with.
I would be happy.
Let's see. Yeah, you have a good way to draw.
But I would need to take your screen share, which I don't know if you want to.
Oh, that's okay, because then
Okay.
where is this stuff? Oh, I guess it's just right here. I always feel like I got to go somewhere else, but it's right there in front of your face the whole time.
Except, well, the problem now, though, Isaac, is I don't know what system you wanted to show. Am I just making one?
I mean, I was going to show that loop that has one state.
Sure, okay.
You know, that's the initial state, and then the only transition is A back to the same state.
Just this guy, right? Okay. All right, so there's our state. So we can label like the states if we want to. I usually label them with integers. That's a 0, I guess. And then the transitions also get labeled. So there's only one transition. So like basically we can start here at state 0 and go around and end up right back where we started and around and around and around. And then we were going to try to solve mu x dot diamond ax, right?
Yeah.
So the equation we have to solve is x equals diamond ax.
Can I posit a potentially true formula for this thing, and then we can talk about it maybe?
Yeah, totally.
So I want to say that this state satisfies the formula diamond A true.
Diamond A true. So that says there exists an A transition. Well, that's all it says. There exists an A transition.
And then also diamond A true, and diamond A true. Any number of diamond A's you want to put there should be okay.
All right, stand by. I'll be back in a few hours. Yeah. Okay. Right. So I agree with that. So, oh yeah, right. So this is what I'm good at, right? Like seeing that kind of stuff. This says like there exists an A transition after which the same equation still holds. So like definitely I can see that this happens, but then like what does the mu mean? I don't really know. And what if I put a nu there? Definitely there's still an A transition after which the formula holds.
Yeah.
Yeah.
I mean, I only know from that Coursera course when he's basically talking about like, you can think about it in terms of finite and infinite iterations, and mu only gives you the finite iterations, whereas nu allows for infinite iterations.
Yeah.
Oh, so maybe for mu, only the first one would be true. Only the diamond A true.
Well, it's a different kind of question. We're asking like, does this state here satisfy this equation?
Yeah.
So the answer can't be like only this one satisfies. The answer has to be yes, it does, or no, it doesn't. You know what I mean? Like definitely this state here satisfies this equation for sure, and all of these. Mm-hmm. But then another valid question is, does it satisfy, this guy?
Okay, yeah.
Yeah, so certainly it satisfies the x equals diamond x, right? That's essentially what writing all of these diamond A's to true was all about in the first place.
Yeah. Right. So okay, so in the video he did something like this. He basically said, like, this is a pretty small system, so we might not see too much interesting here, but like he said, start with x just being the empty set, and then I guess I don't really remember actually now that I think about it. So we were supposed to say something then like,
well, yeah, it's basically like if you were to take an A step from somewhere in the empty set, you would be like back in the empty set, basically.
But what does that mean, from somewhere in the empty set?
It doesn't mean much of anything, quite honestly. There's nothing in the empty set.
Okay, let me try to find something here. Because I remember after the Coursera one, I was like, man, Groot only did like the simplest examples, and I didn't get to here. This was a great one.
You have some different examples. Oh, cool.
Okay, so he used a little different notation. This x min equals, that's your mu x dot, and
cool.
x max equals, which is your new x dot.
Yeah.
So there's this labeled transition system here, and all the transitions are A except this one. This is the only B in the whole thing. And then the states are labeled with integers again, 0, 1, 2, etc.
Mm-hmm.
And so we're trying to ask the question for the initial state, so this is 0, 1. Does it satisfy this formula, which happens to be a recursive one? And so I made my table over here, and he said, start with empty set.
Mm-hmm.
Oh, right. It was different here because this was a more interesting formula that had an or in it.
Mm-hmm.
So yeah, right. So, and by the way, also this act thing, this is how he writes a different kind of true that we didn't talk about actually yet. This means that any action can be taken.
Yeah.
So
including no action,
A or B,
right?
Or one of any of these transitions that exist in your system. So for us, it's just A and B.
Yeah.
Okay. So then the question is, starting from this empty set, what states satisfy this equation? And there's two ways to satisfy this equation, right? You can either take an action and get to one of the states in X. Well, when X is empty, definitely nothing is going to apply. Like that right one isn't going to give us anything.
Mm-hmm.
So maybe that's what I missed over here. We just write, oh, there's nothing that's going to get us into the empty set, so we're done. That's our solution.
Right. Yeah. That's probably the best way to think about it.
Okay, but this one was more interesting because it also had this diamond be true, right?
Mm-hmm.
And there are states that satisfy that. In particular, from state 1, I can do a B transition and then get to a state where true applies.
Yeah.
So then okay, fine. So 1 goes in here. That was not a fixed point, so we have to iterate. So now we try X with 1, and same thing. 1 still satisfies this side, but now there actually are ways we can do actions and get to state 1. Namely, we can go from 0 here. And so we iterate and iterate and iterate, and eventually we get down to here and we reach a fixed point.
Mm-hmm.
And so this is like the minimal solution. And so now that we found the solution, finally we can answer the question, does our initial state satisfy this formula, by just saying, is our initial state in this fixed point set? And it turns out it is.
Mm-hmm. Right.
So the answer was yes in this example.
Oh, that's great. I really like this example because when we were first talking about this last week, we were like, when is the empty set not a minimal solution to a formula? Well, here you go.
That's exactly what I was stuck on for so long.
Yeah.
And even after seeing it now, I was still stuck. But I think this is the difference. This is when it's not just the empty set.
Yeah, right. It doesn't completely hinge on this set X. There's like some external stuff that can be true as well. Mm-hmm.
Okay, so that all made sense. And here's where I got stuck then, because he said like, this is minimum fixed. So we did all that stuff with like starting from the empty set and iterating down to here and zeros in it so it satisfies. And I'm like, dang, I'm feeling good. Like I'm such a smart math guy. And then he goes, this was all for the minimal fixed point operator.
Yeah.
And if you remember, it means finite iteration.
Right.
And he said, if we add a little loop in here, like a self transition from 2 back to 2, then this equation wouldn't hold. And he goes, I'll leave that to you guys as an exercise. And I was like, well, that's exactly what I don't understand. So I'm going to do that exercise. So I tried it, but then I ended up still being confused because it's basically the same system. I added the little self loop. Mm-hmm. I made the table. Everything worked out exactly the same. Like, at some point I could get to state 2 via an A transition, but that was always true, right? I could get there from 0. So like this came out to be the same thing. 0 was still in that set. And I was like, dude, it still satisfies, but I didn't really, something, I don't know. Let's see, what did I say here?
So does the label on the transition from 2 to itself matter much? I mean, I see that you put it as A, but like if it was B, would that make any difference?
I don't think so, because it says for any action we can get back to X.
Yeah, right.
So he wrote the same definition that you did, Isaac, I think, right? So it says S satisfies mu x dot phi if S is in X and X is the smallest set such that X equals phi. That's exactly what you wrote earlier, right?
Yeah, right.
Yeah, so like it sure seemed like this all met both of those definitions to me.
Yeah. Well, do you want to just like go through it step by step and
Yeah.
see
Oh, yeah.
if we
Yeah.
end up
Yeah.
at
Sure,
something
totally.
different?
Yeah, totally. Do you want me to clear out my work in case it's wrong so I don't bias us?
Yeah, all right.
Okay. So, is this what you meant? Like, just run through this again and see what we think?
Yeah. I think this will definitely be helpful for me. I feel like maybe it's true for other people that this would be helpful.
Awesome. Okay, awesome. So we're doing min fix, right? So I'm going to start with the empty set.
Start with the empty set. Cool. And maybe we should just do it for the maximal fixed point as well. You know.
Oh, sure. That's a good idea. In fact, let's just take the whole thing and do another copy of it. Except that we want to do max, I guess, right? Oh, I've never done a max one. So we've got our table. Diamond B true or any action X. So with this time, I think we're supposed to start with true.
Yeah.
Oh,
Start
I don't
with
need
all
braces. I don't
the
need braces around that stuff.
states.
Yeah, right.
Yeah. No braces. True. Oh, geez. Yeah, and that's like whatever. The third true that we've seen today, because that's like true the set of all states.
The set of, yeah, that's the same true you gave us at the beginning, though, right? The formula that all states satisfy.
Yeah, maybe it's the same.
If you spelled it this way, I guess.
Yeah, right, with a capital T.
Yeah.
Yeah. All right.
Yeah,
cool.
I think the set of all states is the same true as the formula that all states satisfy.
Yeah, I'm thinking of your act
This is a different true.
the third. That's the third kind of true now.
What was the second?
Okay, cool.
Oh,
So yeah,
the Boolean value was the
Boolean.
second one.
That's right.
Yeah. Okay, so I guess now
Okay.
we just have to say which states either have a B transition or have an action that get us to any state.
Yeah.
I guess that's every
transition or an action. Yeah, everything except 3. Okay.
I guess I'll write that 0.
And how is 4 in that set?
Because 4 has this A action that can get us back to another state.
Sorry, I didn't see your mouse.
Oh, do you guys see my mouse pointer?
I just see like a little dot.
Oh yeah, here. This one. 4 can get us back to 0 via this transition.
Mm-hmm.
Oh,
so we're
back to 0. Oh.
Yeah, we want to. The thing we're working on is states that have B transitions or any transition that gets us to a state that's in X. And for this first iteration, X was every state.
Oh, so we must. Every state. Okay.
Yeah, since we're doing the max fixed point, we started with X being equal to every state. But we took 3 out of it this time, so now we have to iterate. So of these states 0, 1, 2, 4, so of like basically these ones that are still remaining, now we have the same question. But I think we're done, right? Did we just reach the fixed point?
Yeah, I think basically the only interesting one is 1, and it's only slightly interesting because it has that A transition to a state that's not in our set. But it is true that it has a B transition back into the set, so I think we're good at that point.
Yeah.
And yeah, we certainly shouldn't get a smaller set than our minimal solution, right?
Oh, that's right. Yeah, that's a great point. This was our minimal solution. So if we were going to go smaller, that would be a problem. Great point.
Yeah, for sure.
Okay.
Can you also go through minimal definition?
Yeah, the minimal one. The minimal one was what I had done here, and it was. So it's the exact same transition system. It's the exact same equation. The only difference is this. It's a mu x dot instead of a nu x dot.
So you're starting from empty set.
Right.
Yeah. Right.
So
yeah. And the minimal solution start from the empty set, and then the maximal start from all the states.
Right. So here we have to say, when we start with x as empty set, we say which states either have any action that can get us into a state that's in the empty state. Well, none, obviously. There are no target states that we can even go to, or have a B transition. And so that B transition, this is a B transition. And so state 1 gets added into our set.
Yeah. Yeah, that's really interesting because, in the minimal solution formula, we're always, looking to start from false and then kind of building up from there. And in the maximal solution, we're starting with true and then kind of removing things as they, don't land back in the set according to the formula or whatever. There's something interesting there that I can't quite put my finger on related to induction and co-induction, but I'm not 100% sure what it is.
I have one thing that confuses me, and this was also confusing me in Greg's lecture. So we are starting with for maximum fixed point. We are starting with a set of all terms, and but if we want to exclude something, we must remember what we are excluding. So in that sense, we are doing almost the same thing as the defining minimum fixed point, right? Because we want to have this set for minimum. We have this set that are included in our set, elements that are included in our set, and for the maximum, we have this set of elements that are excluded.
Yeah.
All possible, right?
Yeah. Well, yeah,
I would go ahead to maximum relative entropy, where for the maximum, we're starting with no information, whereas for the minimum, we're starting with basically building from the bottom.
Yeah.
And it's really this two-way causality in a system that we're sort of mimicking, top down and bottom up.
Right.
But on both ends, we don't have any information. When we say I have empty set or I have all possible, like a full set, we don't have any other information. I mean, I see this in like almost the same, but because we don't have any other information. If we exclude something, then we must have this information, right?
Yeah, well, in in the minimal solution case, it's like, we're building up the set in terms of like, oh, I found this thing that definitely satisfies this formula. Like, let me put it in there and then see how that affects everything. And in the maximal solution case, we're looking at like all terms, and then we're like trying to find something that doesn't satisfy and then excluding that, and then now asking the same question about this new set with, one or whatever many elements excluded.
Are we setting bounds?
Okay.
Bounds. I don't think there was any talk about bounds. What do you mean exactly about bounds? Like how many times we're allowed to iterate through the set or something?
Or you mean like some kind of extensional definition when you say all even numbers are excluded?
The I don't have a clear idea. I think there's two aspects to that, but the I'm thinking if you know, from a systems view, the minimal effect and the maximal effect seem to be related.
But if these are dual definitions, they must have like the same thing, they must work in the same way, right? You just have some set of elements that are included or excluded, right?
Yeah, well, I mean, they're dual through something like negation, you know, which is basically just set complementation. Right, because like, you know, adding an element to a set and then looking at the complement is just like excluding that element from the set.
Yeah, that makes sense. Okay, thanks.
Isaac, do you want to present more like material, or we've also got those homework problems from the Coursera that we can take a look at?
Yeah, I was gonna say I guess it's like 13 after 11 right now. But I was gonna say, if we want to talk about this again next week, we can start talking about when we like those regular formulas, when we add like sets of actions as well. I mean, we sort of talked about it in this example where you had all actions possible, but maybe we can actually talk about all the different possible formulas that can arise from different sets of actions.
Yeah. It looks like I didn't take any notes on that one.
Oh no, I thought that was the most confusing part too.
Oh, did you really? I thought the fixed point operators were hard. I didn't think the regular formulas were that bad.
Yeah.
I've seen regular expressions before.
Yeah, exactly.
But they so basically like we can write things like this. So like instead of writing, you know, box A, box B, box A, or whatever, we can write it like this: A dot B dot A. So that's one of them.
Yeah.
They also have the star and the plus notation, so I can do like wait, is that where the star goes?
No, the star goes on one of the actions.
Oh, yeah, right.
Yeah, like
so for 0 or more A's, for all sequences of 0 or more A's followed by a B, then, you know, then whatever, some formula goes here.
Yeah, and apparently that star is called the clean star, if anybody has heard of that before.
Yeah.
And then they also have the plus, so for all like
one or more A's, right?
1 or more A's followed by a B.
Yeah.
For me, this is like a more understandable.
Me too. I thought fixed
regular expression.
Oh, great. Yeah, I mean, it's like XML attributes or something. I don't know. This is just, I mean, this clean star is exactly how the cell multiplicity works in K-framework. So. Yeah.
What other ones were there? They did this a lot.
Yeah, you can have intersections or unions. I mean, and also we can have just straight up sets of actions, like where you don't even need to say specific. We can do complementation of actions. So like, you know, any action from the set that doesn't contain the action A, for example. Yeah, because
for all not A actions.
Right. Yeah, because we can start expressing some pretty interesting properties using this stuff, like your system doesn't have a deadlock, or, you know, something along those lines. I guess we didn't exactly talk about safety and liveness, but they're related to those fixed point operators. Yeah, so maybe it sounds like maybe we have enough to continue talking about this next time if you guys are interested in doing that.
Yeah. I'll do some reading and watch that YouTube video this week.
Yeah, awesome.
The YouTube's about an hour long and is pretty good. The hard part starts about halfway through it.
Cool.
Yeah, Coursera is a lot longer, but is also really helpful too.
Yeah.
I found that one playlist I will share.
Oh, cool.
Oh, great. Yeah. Yeah, cool.
Yeah, awesome. I didn't realize that there was a whole second section to that week 2 of the modal formula stuff. So apparently I have quite a bit more material to go through as well.
Oh no, I thought you were all done with that one.
Well, I was done with the modal mu calculus material, and now it's like actually doing extensions of that stuff with data.
Yeah, nice.
Mm-hmm. Cool. Yeah, so like I was saying, I don't have any K framework stuff really to present this week, but it sounded like you had some stuff, Joshy.
I could show a couple things. I'm just thinking I need to be on my other system though, so I'm not fully prepared. That's my bad.
Yeah.
Tomislav, what were you wanting to talk about?
Yeah, I have something especially for you.
Should I start a separate recording or just let it run?
Yeah, I think let's restart. We're switching gears, right? We're done with modal stuff?
Yeah.